Swayam Prabha. Digital India. Educated India.
Okay, so we talk about implementation attack. So this is basically, so far we have seen for cryptanalysis purpose, we have seen that we are using we are looking at the mathematical form of the crypto system, the mathematical how they build, like for differential attack we try to see whether we can have some differential trials in the input, and then we see whether that we have some output difference also coming with some significant probability, or in the S box or in this linear cryptanalysis or algebraic attack we have seen whether we have some linear relationship between the input between the plain text along with the key with the ciphertext. We have system of equations. So those are basically some mathematical we look at the function of this mathematically, then we have some attacks on that. So this is other type of attack, this is called implementation attack. So it takes on a different approach to the above all discovering the secret key. So this is a different type of attack to discover the secret key. So this is, instead of attacking the mathematical properties of the algorithm, this form of attack take advantage of the physical phenomena that occur when the cryptographic algorithm is implemented in hardware. Suppose we are running a encryption algorithm. So suppose RSA, we are running a RSA encryption algorithm. So then we see when we have a hardware for running for this encryption, or we have a hardware to implement this AES. So when AES is run in this hardware, we see the physical phenomena. That means we look at the power consumption of this, we look at the how much time is taking for each instruction. So these are all physical phenomena. So based on this physical phenomena we try to guess the key. So that is called implementation attack. So we take the advantage of physical phenomena that occur when a cryptographic algorithm is implemented in hardware or software. So this is called side channel attack, like as if somebody is sitting in the side of the computer where or some machine, some system where this physical phenomena are being observed. So that's why it is called side channel attack. Somebody is sitting in the side and observing this power consumption, power fluctuation, or the time delay. So if we have a loop, we'll talk about the timing attack, like when we calculate the exponentiation m to the power e for our RSA encryption scheme. So there, if E is the basically the E is the public key, but when you calculate C to the power d, the Bob is calculating C to the power d to get so C is the m to the power e, that is the ciphertext sent to Bob, and Bob will calculate C to the power d. So D is the secret key of Bob. Now when Bob calculates C to the power d, now it is basically 0 1 bits. Now this is an square and multiply method. So we see, so when we have all this 0, then we will not go for the multiplication. So when that loop has when we have a 1, then we will go for multiplication. So by looking at the time, how much it is taking instruction, so we can guess the key. So that is called timing attack. So that is the physical phenomena that occur when we implement the cryptographic algorithm in hardware or software. So that's why it is called side channel attack, as if somebody is sitting in front of that machine or computer and observing this physical phenomena. Okay, so there are 4 types of side channel attack are listed in the FIPA standard. So the power analysis, this is one of the side channel attack, timing analysis, fault induction, and tempest. So we will talk about mostly this power analysis, differential power analysis DPA, which is basically applied to DES, to break DES, and then we talk about timing attack also in this lecture. So let us talk about differential power analysis. So power analysis is relatively new concept, but it has proven to be quite effective to attacking a smart card or similar devices, because smart card has very low power, I mean the power or capacity, it is very low power capacity. So, this power analysis is first implemented on the smart card, and it was demonstrated by Bolender in 1997, but specific attack strategy was not given. But later on the same it was brought to the general public attention by Kochar and the cryptographic research team in San Francisco. So, they brought this idea of the power analysis for the cryptographic breaking the cryptographic primitives. So, Kochar et al. Provided a attack strategy that would recover the secret key from the cryptographic system running the DES algorithm. So, this is the generalized version of the what is the basically the, but the basic power analysis attack was on the smart card devices. So, we will talk about that device, I mean the. So, this caused great concern amongst the smart card community, and the search for an effective countermeasure began. To date, a limited number of countermeasures has been proposed and none are fully effective. So, the smart card this can be attacked by this power analysis. So, people start off having the countermeasure or to prevent this, but so far there are some attempt is there, but so far not much progress in this proposed or fully effective. The attack works equally well on the other cryptographic algorithm as shown by the Thomas et al., who presented a great deal of supplementary research on this subject. So, power analysis involves an analysis of pattern of the power consumed by the cryptographic module as it performs its operation. So, suppose we are running a cryptographic algorithm, suppose say for example, suppose we are running a cryptographic encryption scheme, we are running an encryption scheme in hardware. Now, this power analysis will just analysis the power consumption it is doing when it is implementing in hardware. So, that is the observation we have to make in power analysis. So, how much power consumption, power fluctuation. So, we have to have a machine to detect that. So, we will come to know the purpose of this pattern analysis is to acquire knowledge about the actual operation that is not readily available though other sources. The power consumption will generally be different for each operation performed, because it will depend on the different operation, because it has different instructions. So, every algorithm. So, suppose we have an encryption algorithm DES, AES, RSA. So, every algorithm has different type of instruction. So, depending on the instruction also the power consumption will be different, and also the different data will give the different power consumption, power fluctuation. So, the power consumption will be different for each operation performed. One of the cause of this variation is the transistor technology used to implement the module. The transistor act as a voltage control switches, and the power they consume varies with the type of instruction being processed. We have said this. For example, a conditional branch instruction appear to cause a lot of noticeable fluctuation according to Kochar. If we have a conditional branch instruction in our code, in our the algorithm which we are implementing, maybe some encryption algorithm, if there is a conditional branch instruction, if there is a conditional branch, then it will have a lot of noticeable fluctuation in the power by according to the Kochar. So, we have given an example of a setup of power analysis in figure 3. So, where is figure 3? Yeah, this is the figure 3. So, this is an example of setup of power differential power analysis on a smart card device. So, here we have a smart card reader, and here we have the connection. This is connected by serially, and this is the PC where we are analyzing we are capturing the power fluctuation signal. So, this is the signal processing technique we are doing. This PC software has this part, these are the feature: smart card control, attack control, signal processing. So, this for smart card and similar devices, the power can be measured across a 10 to 50 ohms resistor in a series with a power or ground line of the specific device. The resistor would be small enough so as not to interface with the operation of the circuit itself, but large enough to give the easily observable voltage fluctuation. So, that we can easily get the power fluctuation or voltage fluctuation. It is better to put the resistor in a series with the ground of the device. If the power line is used, then the two scope probes would be needed and the resultant waveform subtracted. Okay. So, this is the simple device, but this is the device, this is the setup for differential power analysis attack for smart card. We have a general device which will be working on any cryptographic algorithm. So, we will talk about that. So, although the setup, the design we have seen will suffice for smart card, but it will generally not be this simple for complex cryptographic algorithm, which probably draw a power from the peripheral component interconnect PCI. So, we have little more complicated circuit, little more complicated design for this cryptographic algorithm to get the power fluctuation. Ideally, the attacker would wish to get a close as possible to the actual chip performing the operation if the high signal to noise ratio is to be obtained. This might be more difficult than it first appear, as information on which the board numerous chip is actually running on the algorithm may not be readily available. So, even if the power pin of the chip would have been physically separated from the board to perform the attack, then the reattach once complete. Okay. So, most we will come to the figure of that. So, this is basically the general figure than the smart card one. So, this is general figure which is the setup of the differential power analysis for a high speed cryptographic algorithm. So, here this is the hardware to run the cryptographic say encryption algorithm or decryption algorithm, and it may take power from PCI back plane. So, we need to have a extender board. So, which is capturing the power signal, and it is ultimately sending to the this computer, this PC to analyze this. So, this is little more complicated than the simple smart card. This is the simple one. This is the simple smart card power analysis attack on smart card, but this is little complicated because it may take this may take power from the PCI PCI. So, ultimately the signal is going to the PC to analyze. So, this is the so most tamper resistant device would not so this is the figure we have seen. In this case, the PCI extension board is used to measure the power fluctuation. The actual cryptographic board slot into the extender board, and therefore, the power of the cryptographic board draw from the PCI back pin has to flow through the external board, which can be fitted with some point, and that allows the measurement of the power. So, this system can be homemade or one can purchase this system. Okay. So, assuming this setup either 3 or 4. So, we want to apply this on the DES. So, we want to apply this on the data encryption standard algorithm for this differential power analysis. So, for that we have this setup, we have this model, differential power analysis model, we have the chip, and ultimately with this power fluctuation on the power consumption or power fluctuation signals should go to the computer. Okay. To attack on this DES, data encryption standard, this is the differential power analysis on DES. So, basically, so we choose J many plain text randomly. So, this is a chosen plain text attack or the known plain text attack we can say, but this plain text has to be chosen randomly. So, that is why you can say this is a chosen plain text attack. So, we choose j many plain text randomly, and this we are denoting by Pij. So, j is starting from this small j is starting from 1 to j, and so we tried, and then the method must devise the produce a random set of j plain text input, and that can send to the crypto system for encryption. This method must be automated as number of random plain text input will be quite large. Generally, this will be the job of the PC. However, on more complex crypto system, it may be possible to upload the new firmware that will do the trick. Okay. So, basically the ultimately we have the we choose the j many plain text randomly. So, that should be done either by the PC or some complicated or some complex crypto system or some new firmware should able to give that. So, why randomly? We will come to that. Why need this random plain text? Now, we upon receiving the plain text, we ask the board to begin the run the algorithm and draw the and it will draw varying amount of power, because we ultimately want to encrypt this plain text and get the ciphertext. Okay. So, for that it will draw various amount of power. So, this power fluctuation can be sampled using the digital sampling with which should be capable of sampling at about 20 to 30 times the clock frequency being used. There are two major reasons for this. Possible that we might have multiple operation occurring in each clock cycle. Also, operation of interest might only last for a small fraction of the clock cycle, and the more sample you have per cycle, the less chance of noise caused by magnitude of sample. The waveform observed. So, after running this, so we take the sampling digital sampling of the power fluctuation, and suppose the waveform observed when we give the plain text Pij is represented by the matrix W F J K. So, this is a matrix where j and k are used. J is used for the plain text, okay, and we denote this COJ as the corresponding ciphertext. So, we have the plain text P, plain text is denoted by what? Pij, and COJ is the corresponding ciphertext, and this is the corresponding matrix which is called waveform matrix. Due to this, this is the sampling, digital sampling on the power fluctuation. This is the waveform matrix WFIK. Okay. So, now we partition this matrix into into the rows. This is the rows WF0 PK and WF1 PK, and suppose there are P rows which are having this 0 PK and Q rows which are having 1 PK, and such that P plus Q is equal to J. So, we apply it. So, this is the partition function which is denoted by D. So, it will partition the matrix into two sub matrices, this and this. Now, and provided that the input Pij. So, this is the plain text were randomly produced. Then if this input is truly random, I mean if we produce this input randomly, then as j tending to infinity, P and Q will be j by 2, because there will be half that 0, this 1 for 1 the bias occur and 0 bias should not occur. So, the partitioning function allow the division WF, that matrix, because it calculates the values of the particular bit at particular times during the operation of the algorithm. Okay. If the value of the bit is known, then it will be known whether or not the power bias should have occurred in the capture waveform. For 1 bias should occur and for 0 bias should not. So, and that if this is chosen randomly, then this should be half. Okay. Separating the waveform into two separate matrix will allow averaging to reduce the noise and enhance the bias. So, that will do. So, basically this is the partitioning, and if we choose this Pij's randomly, then it will be half basically. So, half of the biased will be half of have 1 and half of will be have 0 with probability half also as j tending to infinity. And this is an example of a partitioning function. This is d ci ck, and this is the last bit k, this is the round key k 16 equal to C1 XOR with S box 1, and the input of the S box is C6 XOR with k 16. So, this is the function coming from DES, where S box is the function that output the target bit of the S box 1 in the last round of DES. Okay, C1 is the one bit of the ciphertext COJ that is exclusively that is XOR with the bit C6, that is the 6th bit of the ciphertext, and that is again after running the S box, that is again XOR with the this C6 is XOR with the last round sub key, and which is basically k 16, and this is of 6 bit. So, we will do the exhaustive search on this 6 bit to get the value. So, let us talk about how. So, 6 bit of the last sub bit sub key, and that is input into the S box 1. Okay. The value of this partitioning function must be calculated at some point throughout the algorithm. Okay. So, if the value C1, C6 and K 16 can be determined, it will be known whether or not power bias occurred in each waveform. So, it is assumed that the values C1 and C6 can be determined, and the value of the K 16 is information sort. So, to find this, we do the exhaustive search on this K 16. So, this is 6 bit. So, there are total possibility 2 to the power 6, that means 64 possibilities, possible sub keys are there. So, we will try this for all sub keys. The right one will produce the correct value of the partitioning bit for every plain text input. However, the incorrect one will only produce the correct result with probability half, because we are choosing the this plain text as random. So, that is why it will give us half. So, in this case, the two set that biased that WF0 and WF1 will contain a randomly distributed collection of waveform which will average out the same result. The differential trace will thus show the power bias of the correct key only. Okay. Of course, this means that 64 different traces are needed, but this is a vast improvement over the brute force search of the entire 56 key. So, if you write it mathematically, so this partition of WFIK can be represented by this, where this is giving us 0 this function, and this is giving us W of F1k, it is giving us 1. So, this is equation 9, equation 10. Now, once the matrix WF0 and WF1 has been set up, the average of each is then taken, producing two wave perform. So, AWF0, this is the average. So, we need to divide it by D. So, we will look at that expression. So, and AWF1 both consistence of k samples. So, we need to divide by k. By taking the average of each, the noise gets reduced to a small level, but the power spike in WF1 will be reinforced. So, however, averaging will not reduce any periodic noise content within the power waveform and inherent to operation of the cryptographic board. This can largely be eliminated by subtracting this average of AF0 and average of this WF1. Okay. This the only waveform remaining will be the one which with a number of bias point identified the position where the target bit is manipulated. So, this is this trace is known as differential trace, and this is denoted by delta dk. So, this is the expression for AF0 and this is the expression for AF1, because there are p many. So, this is the averaging on this, and there are q many of such row. So, this is the averaging on this. So, the difference of their mean. So, we take the difference, that is called differential trace. So, delta of dk. So, if we just combine, if we just write the expression, so it will be in this form. So, if j tending to infinity, then the power bias will be average out the value epsilon, which will be occur as times dk. So, each time the target bit d was manipulated. So, in this limit, the average, so on AF0 and average on AF1 will tend towards the expected value of WF0 and WF1, and the equation 13 and 14 will converge to epsilon and 0. Okay. So, therefore, at time k is equal to kd, there will be a power bias epsilon visible in the differential trace, and at all time the power will be independent to the target bit, and the differential trace will be tend towards 0. So, above will work only if the sub key guesses was correct. For other guesses, the partitioning function will separate the waveform randomly, and the equation 15 and 16 will condense to this 0. Okay. So, as mentioned above, 64 different keys. So, this is the exhaustive search on the sub key. So, 64 different traces are needed to determine which key is correct one. So, theoretically, the one obtaining the bias spike will allow determination of the correct key. However, in reality, the other waveform will contain the small spike due to the factors such that non-random noise of the choice of the plain text, and some statistical bias will be there in the S box. So, this may affect our correct choice of the key. So, generally, however, the correct key will show the largest bias spike, and that can still determine quite easily. The other 42 bits from the last round sub key can be determined by applying the same method to the other 7 S box. Okay. So, this is the attack model. So, now we will talk about the timing attack on the on this. This is also part of the implementation attack. So, timing attack is basically telling, suppose we are running a code in the machine. Suppose, let us just quickly go to the square and multiply method. Suppose we are trying to find out b to the power e mod n. Suppose this type of expression we require. Suppose Bob is RSA, Alice is sending a message to Bob. So, Alice is, so Bob public key is E, secret key is D. So, Alice is computing m to the power E, m is the message. So, that is the C. Now, upon receiving C, Bob is computing C to the power D. Now, D is the secret key. So, this type of expression we need to calculate. So, for this we know this is the square and multiply method. So, we every time we square it and we multiply if there is a 1. So, if we multiply, if we just observe the time in this loop, this is a loop, if we observe this loop is taking more time, then we guess that the corresponding bit is 1. So, this is also a side channel attack. So, this is implementation attack. So, somebody is sitting in the inside of the computer and checking how much time its computer is taking to run this code. Now, if for some time it is taking more, then that means that corresponding bit is 1, otherwise it is 0. So, this way one can guess the bits of this. So, to prevent this, these are the things we need to do: constant exponentiation x time. So, we should take constant time, some random delay we can produce. If it is not multiplying, we can have some random delay. Or blinding means we can multiply ciphertext by a random number before performing the exponentiation. So, this way one can prevent that. So, this is the way we can prevent. We have this random number, we can multiply this to prevent this timing attack. So, this is also an example of implementation attack. Thank you.